Welcome everybody to the beginning of Chapter 2, Section 2.1. Now the list of terms that I have outlined in your notes here are a list of terms that we'll cover in Sections 2.1, 2.2, and 2.3. Today we're only going to look at 2.1. So it's the beginning of linear algebra, which means we'll start off with vectors. What's a vector? Okay, well, you've already seen vectors, you've been exposed to them in Calc 2, so I'm not going to repeat old news. But we will talk about how linear combinations of vectors are combined. So we have a vector 2, 4, we have a vector 1, 1. I'm going to multiply the vector 2, 4 by 5, the vector 1, 1 by 3, and what do I get? Well, you multiply each one of these pieces independently, so this is going to be 5 times 2 plus 3 times 1. That's 10, that's 13, and that's the components of your resultant vector, the first component of your resultant vector. On the bottom side, you get 5 times 4 plus 3 times 1. 5 times 4 is 20. This is 23. Okay, so no news going on there. What combination of these vectors, 2, 4, and 1, 1, add up to 15, 27? Okay, so instead of 5 and 3, what would we multiply the vector 2, 4 with paired with the vector 1, 1 to get 15, 27? So we don't know what these coefficients are, so we'll treat them as unknowns. Call them A and B. We want this to equal 15, 27. All right, so we get 2a plus b is equal to 15. We get 4a plus b is equal to 27. Now with systems of equations, we can subtract the left-hand sides and the right-hand sides, and we know that the resultant, well, what we get from the resultant, negative 2a minus 4a is negative 2a. B minus b is 0. That's the whole idea why I subtract the 2, so the b's would cancel out. We get 15 minus 27 is negative 12. So we get here a is equal to 6. And if a is equal to 6, we go back to either one of these equations, 2a, so that's 2 times 6, plus b is 15. So it looks like b is equal to 3. And the combination of 2, 4, and 1, 1 that combines to 15, 27 is going to have a coefficient of a on the vector 2, 4 and 3 on the vector 1, 1. So it'll look something like this. 6 times 2, 4 plus 3 times 1, 1 is equal to 15, 27. So if we were to write the above as a system of equations, then you would do it exactly as we did here. 2a plus b is 15. 4a plus b is 27. Okay. Now, systems of equations can be written in terms of matrix equations. So let's say I had a system of 3 equations and 3 unknowns, x, y, and z. 2x plus 3y plus 7z is equal to 4, minus 5x plus y plus 8z is equal to 2, 6x plus 12z is equal to negative 15. To write that in terms of a matrix equation, you pick off the coefficients on x, y, and z, write them in order. Okay, this one, the coefficient on y happens to be 0, and so that's why there's a 0 there. And in each one of these equations, we have the coefficient on x that comes first, y that comes second, z that comes last. So we will write the vector here, x, y, and z. Okay, so you'd have to, if this weren't the case, and this was y minus 5x plus 8z, just rewrite the 5x, the negative 5x, and the 1y, so that the x always comes first. That's how you make this a true statement. Now, This is a matrix equation. We can further abbreviate this by making an augmented matrix. So this is an augmented matrix. Okay, put a little dashed line right there. Okay, this is a 3 by 4 matrix because there's 3 rows and 4 columns. Each number is an element. Okay, the A sub ij is the ith is the element in the ith row and jth column. Okay, so if we look at the A11, that's the first row, first column. Okay, the vector that's in the first row, first column here is 2. Okay, what about second row, first column? That's -5. First row, second column, that's 3. Second row, third column. Okay, second row, third column, that's 8. First row, third column, that's 7. Second row, fourth column, that's 2. And third row, second column. Third row, second column. That's 0. Now, a matrix could have row vectors and column vectors. Okay, there are 3 rows to this matrix, so it can have 3 row vectors. Okay, we typically signify them with the letter B. So there's B1, that's the first row. There's B2, that's the second row. There's B3, that's the third row. Okay, and the vectors are written laterally because they're representing row vectors. Okay. As far as column vectors go, there's 4 columns to this matrix. So this is the first column, the second column, the third column, and the fourth column. Okay, and we represent them with the letter A. All right, moving right along here. The transpose of a matrix is denoted A superscript T, that's A transpose, and is obtained by writing the rows as columns and the columns as rows. So in general, what you're looking at is you're writing the transpose of the matrix A, or the Aij element is Aji. So that means looking at, I shouldn't say this. Oh no, because I'm referencing the vector, the matrix above. Sorry about that. So the matrix A was 2, 3, 7, 4, -5, 1, 8, 2, 6, 0, 12, and -15. So if I were to take the transpose of that matrix, this first row becomes my first column. So we get 2, 3, 7, and 4. The second row becomes the second column, -5, 1, 8, and 2. And lastly, 6, 0, 12, and -15. So this is a 3 by 4 matrix. This is a 4 by 3 matrix. Okay, and you can see how I retrieved A transpose. A square matrix has the same number of rows as columns. Okay, so this is a 3 by 3 matrix, 3 rows, 3 columns. Okay, the main diagonal of a square matrix consists of the elements A11, A22, A33. Okay, it's the Aij element where I equals j. So looking at this matrix, the main diagonal is 3, -2, and 12. The trace of the matrix is the sum of the entries on the main diagonal. So it's what you get when you add up A11, A22, A33, and so on. So in this case, it's 3 plus -2 plus 12. That's 15 minus 2. That's 13. All right, so a matrix is upper triangular, okay, if it's all the entries above the diagonal are 0. And it's lower triangular if all the values below the diagonal are, it's lower triangular if all the values above the diagonal are 0. So this is lower triangular because on the main diagonal, 4, 6, 1, negative 9, all the entries below it are 0. This is upper triangular because on the main diagonal, 8, 6, 5, negative 9, everything above those entries are 0. You're working with a diagonal matrix, which will be important in the long run. A diagonal matrix has zeros above and below the main diagonal. Now, that doesn't mean that there can't be a 0 on the main diagonal. That's fine, okay? But everything below the main diagonal must be 0. Everything above the main diagonal must be 0. Anything on the main diagonal can be anything it pleases. Okay. A symmetric matrix is one where A transpose is equal to itself. An anti-symmetric matrix, or which we'll call skew symmetric, is such that A transpose is equal to negative A. Okay, so here we have two matrices. Okay, let's see if they are skew symmetric, symmetric, or none. Here we go. Let's call this A, and let's call this one B. So what's A transpose? Okay, so I'm going to take the row 7, 5, 2, and that's going to be my first column in the transpose matrix. I'll take the row 5, 8, negative 4, and that's going to be my second column. And I'm going to take the third row 2, negative 4, 3, and that's going to be my third column. Okay, question. What is the matrix A that I just wrote down? It's 7, 5, 2, 5, 8, negative 4, 2, negative 4, 3. Is that the same as A transpose? Okay, 7, 5, 2, 5, 8, negative 4, 2, negative 4, 3. It is. So in this case, A transpose is equal to A, so this is symmetric. Okay, what about B? Let's see. Let's look at B transpose. Okay, so the row 0, 8, negative 3 now becomes my first column, 0, 8, negative 3. The second row, 8, 0, 5, becomes my second column. And the third row, negative 3, 5, 0, now becomes my third column. Ask yourself, is B equal to B transpose? 0, 8, negative 3, correct. 8, 0, 5, correct. Negative 3, 5, 0, that's correct. Very good. So this is symmetric as well.